My name is SHAZWAN. Allow me to start our discussions right now. So, what is differentiation? Differentiation refers to the mathematical process of finding the derivative of a function with respect to an independent variable, which is we're going to differentiate the unknown number that we replace with the variable to solve out the problem. There are several types of application of differentiations that we learn in this semester, including related rates, analysis functions 1 and 2, maximum and minimum problems, and loss terms and mean value theorem. In this video, we're going to discuss one of the applications of differentiation, which is maximum and minimum problem of differentiation. So, what is maximum and minimum problems of differentiation? Maximum and minimum problem of differentiation was defined as the maximum of functions as the highest value that is reached over a class interval. Similarly, the minimum of a function is the lowest value that's reached over a class interval. Applications of maximum and minimum problems of differentiations in our daily life could be seen in a few different sectors, such as economic and finance sector and engineering sector. In economic and finance sector, the applications needed to calculate the value of interest and loss taken from investment. In the engineering sector, they need this type of applications to help them to calculate the value of the cost needed for their own construction.
Allow me to proceed to the first problem statement. A farmer has 200 meters of fencing and wants to enclose a rectangular area along the side of a barn. Question 1a, show that the area is 100W minus W squared. And question 1b, what are the dimensions of the rectangle that maximize the enclosed area? For solution 1a, the first step we need to do is define the variables. In this case, we can define the width of the barn as W and the length of the barn as L. For the next step, we have to write down the constraint. And in this case, we write down the perimeter of the rectangle, which is given by the equation 2 times in bracket L plus W equals to 200. For the third step, we express the quantity to be optimized. The area of the rectangle A is given by the equation A equals to L times W. For the fourth step, we solve the constraint equation for one variable, and in this case, we solve for L in terms of W. 2 times in bracket L plus W equals to 200, and then we expand the bracket by multiplying 2 with L and 2 with W, so then we will get 2L plus 2W equals to 200, and then we divide the entire equation with 2, and then we will get L plus W equals to 100. Finally, we move W to the right hand side, thus getting the final answer of L equals to 100 minus W. For the fifth step, we substitute the expression for L into the equation of the area, which is L times W. The value of L, which is 100 minus W, will be substituted into the equation, and we will get A equals to in bracket 100 minus W times W. And finally, we expand that bracket by multiplying W with 100 and W with W. So then we will get the final answer of A equals to 100W minus W squared. As for question 1b, the first step we need to do is find the derivative of the area with respect to the width. We take the equation of the area, which is 100W minus W squared, and we differentiate it. So then we will get dA over dW equals to 100 minus 2W. For the second step, we set the derivative equals to 0 and solve for W. 100 minus 2W equals to 0, and we will move the 100 to the right hand side, and we will get negative 2W equals to negative 100. And then we make the equation positive by multiplying it with negative 1, and then we will get 2W equals to 100. Finally, we divide the entire equation with 2, and then we will get the final value for W, which is W equals to 50. For step 3, we check for the maximum with second derivative. In order to do this, we take the derivative that we obtained earlier, which is 100 minus 2w, and we differentiate that derivative further, the second derivative, and then we will get the answer of negative 2. And from here, we can see that negative 2 is less than 0. So, we can confirm that w equals to 50 is the maximum value. As for the fourth step, we substitute the value of w back into the equation for L. The equation L equals to 100 minus w, and the value of w, which was 50 that we obtained, we substitute it and we will get L equals to 100 minus 50, and we will get the final answer for L being 50. As for the final step, we write the final answer that we obtained from the values in the entire solution. In this case, we got W as 50 and L as 50, thus answering question 1b.
Next, we proceed to problem statement 2. The question is, a cylindrical container with a full volume of 2000 cubic centimeters is to be made. Find the dimensions that minimize the surface area of the container. First step, we need to define the variable. So we have cylinder at here, which is the container, and then we just label H for height and R. Second step, we need to write down the constraint. For this question, we need to write down the volume of the cylinder that is given by, which is V equals to pi R square, H equals to 2000. Next step, we have to express the quantity to be optimized. For the equation, we need to write down the literal surface area, which is 2 pi RH, the two circular bases with an area 2 pi R square, and the total surface area A is given by A equals to 2 pi RH plus 2 pi R square. Step 4, we need to solve the constraint equation for one variable. Based on the equation, we need to solve H in terms of R. So first, we write down the equation, which is V equals to pi R square H, and then we move pi R square to the left and will be divided with V, and we get H equals to V over pi R square. Then we fill the value of V, which is 2000, and finally we will get H equals to 2000 over. Next step, we have to substitute the expression for L into the equation of the area. First, we have to write down the equation for area, which is A equals to 2 pi RH plus 2 pi R square, and then we substitute the equation of H into this equation, and then we get A equals to 2 pi R times 2000 over pi R square. Step 6, we need to simplify the equation of the area. So first, we write down the equation, which is A equals to 2 pi R times 2000 over pi R square plus 2 pi R square. Then we simplify the equation and we get A equals to 4000. For step 7, we need to find critical points of the function A brackets R. To find the critical points, we need to differentiate A brackets R with respect to R. So we write down the A over the R equals negative 4000 over R square plus 4. For the next step, we need to set derivative equal to 0 and solve. So first, we write down the A over the R equals to 0. Then we substitute the value and we get negative 4000 over R squared plus 4 pi R equals to 0. To solve this equation, we need to move 4 pi R to the right and we get 4 pi R equals to 4000 over R squared. Then we move R squared to the left and we get 4 pi R cubed equals to 4000. Then 4 pi, we move it to the right. It will be divided with 4000 and we get R cubed equals to 1000 over pi. And lastly, we move power of 3 to the right. It will be square root 1000 over pi and we get R equals to 6.37 centimeters. Step 9, we need to check the second derivative to confirm the value of R is right. So first, we need to differentiate dA over dR. Then we get d square A over dr square equals to 8000 over R cubed plus 4 pi. Then we substitute R into the equations. So we get the positive value, which is 794.61. So we confirm that 6.37 centimeters is the minimum. For the next step, we have to substitute the value of R back into the volume equation to get the H value. So first, we write down the H equation, which is H equals to 2000 over pi r squared. Then we substitute the value of r into for last step, which is step 11. We just need to write the final answer. So we get r equals to 6.37 centimeters and h equals to 15.69 centimeters. At the end of the discussions, we have solved all the problem and find all the answer for all the questions. For problem statement 1a, we know the area is 100W minus W square. And for 1b, we know the dimension that's maximum, the enclosed area, are a length of 50 meters and width of 50 meters. For problem statement 2, to minimize the surface area of the container, the cylindrical container should have a radius of approximately 6.37 centimeters and a height of approximately 15.69 centimeters.